Everyone, thanks for joining GenScript webinar session today. This is Irene, Product Manager from GenScript, handling NGS reagents and oligos. Today's topic is Unleash the Power of Target Next Generation Sequencing by Semiconductor DNA Synthesis Technology and a Novel Chemistry. I'm very excited to present to you today Dr. Josh Wang. He is a senior scientist in the Research and Development Group in GenScript. He joined GenScript in 2019 with a background in NGS product development and bioinformatics. At GenScript, Josh focuses on developing groundbreaking NGS ideas and the technology that bring lasting impacts to the research and the clinical field. He holds a PhD in genetics from the University of Rochester and a master's degree in statistical genetics from Columbia University. So this webinar is around 45 minutes. And if you have any questions, please feel free to type in the questions field below. Your questions will be answered after the presentation. And if we did not get the chance to answer your question during Q&A session, we will email back to you the answer. And we will also record this webinar and will be available for viewing in a couple of days. And at the end of the presentation, we will talk about our free custom panel promotion. And the number of spots is limited, so please stay tuned about the details. And we also have a webinar for COVID-19 rapid antibody discovery B-cell screening on June 2nd, next week. So please feel free to sign up on our website or via the email link if you are interested. And without any further ado, let's welcome Dr. Josh Wang to start his presentation.
Thank you, Irene. Thank you, Irene, for the very kind introduction. And hello, everybody. A huge welcome to all of you for joining us today for our webinar series. I hope everybody, your family and friends are all doing well and staying well. My name is Josh Wang. I am a senior scientist with GenScript R&D. It is my pleasure today to speak about GenScript Next Generation Sequencing Services and our core technologies. The title of my presentation today is Unleash the Power of Target Next Generation Sequencing by Semiconductor DNA Synthesis Technology and Novel Chemistry. Here is the outline of my presentation today. I will start with some broad introduction on next generation sequencing, or NGS, and Targeted NGS. I will then introduce our unique solutions and positions and how we might help you tackle your research problems better. This includes our GenFisher Target Enrichment Solution and our NGS library preparation solutions for Illumina platforms. If any of these products interest you, please go check them out on our website, as we are running a free trial program that is first come, first serve based. So, okay, let's get into it. I assume you have heard or possibly have worked with GenScript before, but in case you have not, GenScript is a global contract research organization that specializes in reagent services and products. Since its founding in 2002, our gene synthesis services, GenScript has gone through many milestones. Not only have we expanded to more geographic areas around the globe to better service the local research communities, but we have also enlarged our service areas to regulate oligosynthesis, protein and peptide services, antibody production, and even more. We are now proudly serving more than 110,000 customers globally, and is the #1 gene synthesis service provider in the world. At GenScript, we have always committed to bringing our experience and expertise to the research community and to the research frontline to provide researchers with the best services and products and fast. For example, to help researchers and clinics battle the COVID-19 pandemic, GenScript team worked around the clock to have developed detection and research toolkits in January of this year. It was very well received by the research community. Examples like this really speaks about our commitment to providing the best and timely solutions when they are needed. One area we have recently entered, as you can see on this timetable, is the next generation sequencing reagents field. Today, I will focus on them and introduce to you where we are positioned to hopefully address some of the unmet needs that could really benefit the community and help you advance your science. I'm sure everybody here knows about next generation sequencing, or NGS, but just as a refresher, the next generation in the term next generation sequencing is relative to the first generation sequencing, which is Sanger sequencing, as is shown here. Sanger sequencing is a way to read nucleotide composition of a DNA fragment by incorporating fluorescently labeled dideoxynucleotide during in vitro DNA replication. Another name of NGS is actually massively parallel sequencing, which to me is actually a more accurate name. So what NGS really means is run lots of Sanger-like processes at the same time. The sequencing chemistry varies among different NGS platforms, some of which are listed here, but the underlying idea is the same, that is to parallelize many sequencing reactions in a confined space to retrieve DNA information quickly and comprehensively. So different companies and technologies have their own advantages and disadvantages and may fit some applications better than others. But among all the sequencing instrument providers, Illumina is the dominant player and the most widely used one. For the sake of today's presentation, I will focus on Illumina's platforms, and also for simplicity, unless I point out otherwise, all my examples will refer to the human genome and the human DNA. The same principle and examples, though, should apply to all genomes and to all organisms. As I will focus on Illumina platforms today, I'll briefly introduce it. Here is a lineup of Illumina sequencers. Some are outgoing, but they vary in size and amount of sequencing data they generate. But all instruments use the same underlying chemistry, which is very similar to Sanger sequencing and called sequencing by synthesis. Very quickly, it starts with NGS library preparation, a process that attaches specific sequences to the DNA sample so that they can be amplified and subsequently read by the machine. Next, these molecules are loaded onto a carrier called flow cell, where bridge amplifications happen. It is a process that copies the DNA library information onto the flow cell through the sequences attached in the first step. A flow cell contains millions of positions, or officially called clusters, for library molecules to land and get copied, thus providing the massive parallelization. Next is the sequencing step. The copied DNA on the flow cell serves as the template for Sanger-like reaction to happen, and DNA sequences are read from each spot on the flow cell. Last is to transform the reading from the machine to nucleotide information and start to perform scientific analysis. So we just quickly went over some technical background of NGS in general. So in terms of its application, I think everybody would have their own opinions. But for me, with a human disease and genetics background, NGS is a really powerful tool to search for low frequency mutations and do that in a large population very easily. So when it comes to mutations and diseases and genetics and diseases, not only does NGS enable detection of harder and rarer mutations detections or detecting more deeply, it also provides the possibility of review information more widely, or in other words, it provides a bigger picture of an individual by surveillance of his genome. That's why there's been so much talk about NGS being the basis for precision medicine. The hope is that we move from symptom-driven medicine that was universally used in the past to the whole population, and also move from clinical trial-driven medicine where selected individuals or average patients got to represent the whole population to a state where we could perform more comprehensive diagnostics and precisely treat individuals based on their genetic code and sophisticated prediction algorithms. The first step, however, for all of this is of course sequencing and to decipher the genetic codes. I won't expand on them, but there are some areas where NGS is heavily used in precision medicine. And also, as an honorable mention, in the US, the White House launched the Precision Medicine Initiative in 2015, the goal is to ultimately be able to treat the right patient with the right drug at the right time. So to me, there is no doubt that sequencing will be part of this ongoing effort and many others to come. Another factor that contributes to the accelerating popularity and adoption of NGS is lowering cost. This diagram, taken from the NIH Human Genome Research Institute website, shows the cost of sequencing per megabase of DNA. You can see the price has dropped 1 billion times since about the time the Human Genome Project completed in 2002-2003. But the drop became significantly faster in the last dozens of years. There has been a positive feedback loop to me between creating more applications using NGS and better NGS applications driving the technology forward and the price down. So I personally believe that this trend will continue. And equally, I believe NGS will enable us to do even more and greater things. As great as NGS is as a technology, there are challenges that require more technological development. First of all, the cost of sequencing is still at a level that's prohibitive to most. This is especially true for those who are interested in detecting low-frequency mutations, for example, like at 0.1% level, where high coverage is really a necessity. Imagine a 3 billion base pair human genome at 100x coverage. I don't doubt it's achievable, but I don't think there will be many people who can afford it, let alone a 500x coverage whole human genome. In addition to the sequencing cost itself, there are other steps that make the overall bill bigger, like making the libraries, QC the libraries, cloning the libraries, and also with more powerful sequencers and more data coming out of them, data analysis is becoming a very visible cost. These costs combined could drive some researchers who could really benefit from NGS to other tools. Next on the list are errors. The error rate per base level on Illumina platform, which is actually the better one among sequencing platforms, about 1 in 1,000 bases. The overall error rate, if considering errors accumulating at sample preparation step, library preparation step, and even downstream data analysis step, will be at a magnitude of 1 in hundreds. The error rate is not good enough for some field. But there have been ways to mitigate these errors, and we will touch briefly upon them later in this presentation. Last but not least, portability and turnaround time are not really the strongest assets for NGS instruments. So for time-sensitive matters like detection of a virus or disease, that requires a quicker turnaround time, NGS, at the current moment, will not fit the situation well. As you can see, most of these challenges require technological breakthroughs, but to better advantage of NGS, one way to make costs less of a problem and high coverage possible is to steer away from whole genome sequencing, but instead focusing on selected regions of the genome. So for disease research and diagnostics, target sequencing is really a popular choice. There are many ways that people select regions of genome to sequence. Here I'm only introducing the most common two. Those are hybrid capture and amplicon sequencing, as shown in this diagram. In this example, suppose we would like to select to sequence exons 2 and 3. If we choose to use hybrid capture method, we would make an NGS whole genome library and subject the library to bioalternative probes that are designed to anneal with NGS molecules that contain exons 2 and 3. Then through the biotin strep-avidin interaction, we could pull down the selected NGS molecules for sequencing. If, however, we choose to do amplicon sequencing, we basically just use pairs of primers to amplify exons 2 and 3, while using the PCR process to add necessary sequences. Hybrid capture and amplicon sequencing have their pros and cons. For example, capture is really large region friendly and creates less bias, but it does take longer to complete the process. And amplicon sequencing is really good for small targets and is really quick and easy to do, but has these PCR associated biases. A lot of the success secret for amplicon sequencing relies heavily on the quality of primer design. So that will not be my main focus, although GenScript is very capable to help our customers design and manufacture primers. My focus today will be on hybrid capture target sequencing. So with that, I'd like to expand a little bit more on that, particularly its challenges. I just talked about how the technology works, shown in more detail here on the left, where we have sample collection and DNA isolation, making whole genome libraries, biotin probe hybridization, Shiva evidence capture, sequencing, and analysis. A few challenges remain to date are, first of all, the probes. The biotin-related probes that are new to targets. The quality and quantity are too important to be at the level they are in the market. And secondly, most design tools available on the market are just naive tilers. They don't take into account the complexity of our genome or any genome. So a very important thing to bear in mind for successful target enrichment experiment is that not only should we care if we have selected the right targets, but we should also care if the pull down is even. If it's not even, it leads to wasteful sequencing to accommodate the lowly covered regions to bring them up to a useful level. So challenges 1 and 2 relate to this point. A third challenge is that a hybrid capture experiment is rather long, typically taking more than a day and involving lots of hands-on time. This and the last one, poor reagents and protocols, make hybrid capture really hard to be automated, which hinders the wider use of this technology in clinical space. At GenScript, we have been working really hard on addressing the first 2 challenges, which I will present today. We are also actively working and seeking solutions for the rest. Okay, as I mentioned, here at GenScript, our R&D has been working on providing our innovative solutions to the challenges in NGS and Target NGS. Fortunately, we have had some answers in the areas listed here. I will primarily focus on our hybrid capture target enrichment solution today. And we'll touch a little on our library kits. But we are always here, if you need to get more information about anything mentioned in this presentation. So please feel free to contact us. And to kick things off, I would like to first introduce the core technology that underlies our hybrid capture solution. We call the GenFisher work suite, which is our NGS hybrid capture workflow. This core technology is GenScript proprietary semiconductor DNA synthesis. This semiconductor technology is very similar to the technology to make computer chips, cell phone chips, and other electronic devices. It enables us to synthesize thousands of oligos on these chamber-enclosed platinum microelectrodes on a chip all at once. By controlling the electricity passing through each of these electrodes, we are able to select the chambers to be activated. Therefore, we can precisely and confidently grow only the oligo chains that we intended to do so on those electrodes. And currently, there are 2 chip sizes that we are offering to synthesize oligos on. One has the capacity of growing 12,000 oligos and the other 90,000. To better put what I have described, I want to show that in a more graphic way. Here is a short clip that I hope could better illustrate how the technology works. As I mentioned, the core of the high throughput synthesis is the CMOS technology. Here it is showing arrays of chambers within the semiconductor chips. These chambers contain the electrodes on which the oligos are grown, as well as the components that ensure precise reagent delivery. Electronic activation of individual electrodes creates a transient acidic environment, which deprotects the oligo and adds single nucleotide to only the intended oligo. And adoption of the latest semiconductor technology has expanded our synthesis process from 50,000 oligos in a square centimeter space to 150 million. And such large-scale synthesis of oligos and genes transforms our ability to create novel biomolecules, networks, organisms to really advance diagnostics and therapeutic innovation. With that, let's take a look at what the synthesis quality is. Here I'm showing you a distribution of oligos synthesized on our 12,000 oligo chip. They were 125 nucleotides long. The synthesis was completed in a business week and was subjected to Illumina NGS quality control. The figure shows you the NGS result, where you could see that all 12,000 oligos are quite evenly distributed. The NGS also showed that we were able to detect 99.74% of all the oligos we intended to make, with an average error rate of 1 in 370 bases. The interdecile ratio, which is the NGS coverage of the oligo at the 90th percentile over that of the 10th percentile, is 1.98. It is our way of monitoring the uniformity of our oligo pools. Just as a reference, a pool typically is considered uniform with a high single-digit measurement of this metric. So we were very excited to see a number that's really a step up from previous technologies. And again, here is a summary of what we believe contributes to the efficiency of our synthesis and what we can do with it. Our chambers are precisely controlled and enclosed and provide an enclosed environment. And that really benefit our synthesis to have high uniformity and high accuracy. Because we can plant a large number of chambers on our chips, we offer a fast and very efficient synthesis. And that provides us with cost benefits as well. Here are some additional examples of applications that high-quality oligo pools enable, like antibody, protein, and pathway engineering, CRISPR-Cas genome editing screen libraries, genes and mutation assemblies for gene therapy, etc. A precisely controlled and non-contamination and fast system to make oligos is really a foundation to ensure the success of these investigations. Now let's refocus on NGS and see how we are applying this awesome semiconductor DNA synthesis technology to target NGS. As I mentioned earlier, one way to select targets for NGS is by hybrid capture. And the core of that is, of course, the probes that match the sequences of the genomic regions of interest. Naturally, we do that synthesis with our semiconductor chips. Again, we call our NGS capture system GenFisher, and the probes are called GenFisher probes. Here's what we do. Starting from the very left of this diagram, thousands of oligos that carry the probe information are made in parallel, quickly and precisely. After they are removed from the chip, they are subjected to PCR with biotinylated primers to become actual target enrichment probes. At this point, these biotinylated probes are ready to hybridization and capture with pre-made whole genome NGS libraries, which will then give rise to selected targets for sequencing and analysis. Since our semiconductor chips synthesis gives really uniform and accurate oligos, as I showed, the resulting NGS target selection panel came out of the process with extremely high uniformity and accuracy as well. This will translate to strong and even capture of the regions of interest. Now let me show you an example of that, but I wanted to show that with some context. And here's the context. Here is a list of capture probe synthesis technologies. These probes can be single-stranded DNA probes. They can be RNA probes that is transcribed from synthesized and cloned DNA. They can also be double-stranded DNA that's made either by inkjet DNA printing technology or the semiconductor technology I have been talking about. So I won't go into details of each of them, but I have listed some of the characteristics for your reference. So all similar NGS capture probes available on the market currently are based on one of these. So the data I show on the next slide will show you examples of each. So at this point, I do want to mention that GenScript has the capability to make both single-strand DNA probes and semiconductor-based double-stranded probes. But with what I will show, we believe that semiconductor is the superior way to producing these probes. Okay, with that in mind, let's look at this piece of data. Here I'm showing you how the GenFisher probe capture compared to hybrid capture pools made with other providers and technologies. The panel from each provider targets the exactly same 800 kb region in the human genome, and the experiment was performed based on the recommendations provided by each provider. Here, the x-axis shows the various providers and their capture probe synthesis technology, and the y-axis shows the capture efficiency measured by on-target base percentage. It is defined as the percent of sequenced bases matching the desired target regions. The blue bars show the raw on-target percentage, while the orange bars will consider a base as on target if it's within the 150 nucleotides padding regions of the target, because a captured NGS library molecule may overlap only partially with the probe. As you can see, for this specific capture panel, the probes made with GenScript's semiconductor technology provided the most efficient capture performance, with a padded on target of close to 90%. Comes next is the single-strand DNA probes with pretty strong performance as well, at around 80% on target. Others gave variable but significantly worse capture performance. Although we acknowledge that the differences in capture performance will vary with the target regions, we believe this comparison still demonstrates that our semiconductor synthesis used for NGS probes is an excellent solution to NGS target selection. Here I'm showing you the uniformity performance of our GenFisher probes. On this figure, the x-axis is the coverage depth, and the y-axis is the percentage of bases covered at that certain depth. A uniform capture would show consistently high percentage above a certain coverage depth and a steep drop below that coverage, as is the trend shown, as is in the trend shown in this figure. Vendor T here is a recognized leader in creating uniform NGS capture pools, and you can see the GenScript panels closely match to it. As shown on the figure on the right, is the comparison of capture efficiency at per probe level for the two independently synthesized capture pools against the same target region by GenScript. It shows that our semiconductor synthesis and subsequent probe manufacturing process guarantee high batch-to-batch consistency. Now I would like to show you some data collected by one of our early customers. This customer wanted to test our capture probes to benchmark with the solution they had been using. So they were experienced users and they had expectations when they reached out to us. It is against the same 800 kb region I just mentioned, and the customers performed multiplex capture, where they mixed indexed NGS libraries prior to carrying out the hybrid capture experiment. In this case, 4 libraries were mixed in one capture. And on the top left figure, it is showing the on-target performance. Our panel stood at around 65 non-padded on target, comfortably exceeding the 50% on target our customer expected. On the top right corner, it is showing the duplicate rate metric, where it tracks how much reads in the sequencing are duplicates of each other. And those won't be informational in terms of mutation calling and subsequent steps. Usually the lower the duplicate rate, the better the capture pool is. So it measures the probe quality and uniformity. Our panel came out at around 10% duplicate rate, while our customers expected around 25% based on their previous experiences. And when it comes to uniformity, shown on the bottom right corner, our customer measured the bases covered by at least 0.2x the mean coverage. And once again, we exceeded their expectation of 90% by being at around 95%. I hope that the data from our own and from our customer have demonstrated that GenFisher capture probes offer a novel solution to NGS hybrid capture that provides excellent probe quality, quantity, and uniformity. Now I'd like to switch gears slightly and talk about the work we have done to improve the way capture probes are designed computationally. As we have seen that against the same target regions, probes from different synthesis technologies show different performances. We have also internally proven that when adjusting for regions and technology, the placement of the probes also has a huge impact on the final capture performance. And here's how it works in general. Since we haven't have an official name and haven't officially launched the tool, I'm using the generic name of AI capture probe design tool for now. Let's have a genomic region. So conventionally, probes are designed to cover the target region end to end. And each base in the target region is covered once. The more sophisticated tools will screen for some repetitive regions, and that's it. And that's also how we started it, 1x tiling. And we designed a few panels and made them using our semiconductor synthesis, quick and easy. With them, we generated data, and we generated a lot of data with normal and changed probe and normal and changed experiment conditions. We then analyzed the data carefully and used the features of the probes and also used the capture data each probe generated and also their interactions to feed into machine learning models. With the resulting model, we designed more probe panels and repeated the experimentation process and later refined our models. And after a few iterations, the model and the features within the models got stabilized, and that gave us the tool we are currently having, and basically this black box that we use to design extensively for ourselves and for our customers. And the end result of this black box or this model is twofold. The first is that we are able to better design probes against a target region. Given the context of GenFisher capture workflow and experiment conditions. Then extremely simplified example is shown here. So the same target, instead of 1x naive tiling, our tool is able to judge the features of the target and place the probes at the best positions according to its judgment, with the possibility of elevated or decreased coverage. And the second benefit of this design tool is that we could predict accurately how a pre-designed panel should perform in our system. And speaking of predicting performances, even with the most sophisticated tool, it's impossible to get the perfect capture panel the first time, although I believe our AI tool is pretty close. When it happens that there is a need for spiking in more probes to a synthesized panel, GenFisher workflow is really good and flexible with it. As I mentioned, GenScript has the ability to make both column and semiconductor chip oligos and probes. Here I'm showing you the data we have collected when we combined the two. The blue bars here show the non-padded on target percentage, and the orange dots show the above 30x coverage depth base percentage. Again, a metric for uniformity. The first data point is a panel of 8,000 probes solely made by our semiconductor chip technology. And the second is the same probes, but with a combination of 80% probes randomly selected to be made by chip and the remaining 20% by column. The third is the same as the second, except that the remaining 20% was made by a second chip. You can see that all three ways of making and mixing probes gave nearly identical results, indicating that spiking additional probes into a working system is feasible and does not have a negative impact on this system. So one route we recommend to our customers is to use our AI design tool to design and synthesize a panel with our chip technology, which is really fast and inexpensive, great for research purposes. If there is additional need for probes, supplement in column probes, as it's quicker and easier when the number of oligos required is low. When the design is locked, we can remake the entire panel again using our chips. With our technologies, with our combined technologies, I should say, this entire process of optimization could still potentially be shorter in terms of time it takes to compared to if you get the capture probe panels from other providers with other technologies. And because of that, with a few conditions and limitations, we actually offer one round of free panel optimization to our customers who order capture panels with us. And this is something to me really speaks to our commitment to our research community and our confidence in our AI design tool and our technology. So now I would like to quickly summarize what I've talked about so far. GenScript hybrid capture probe tools made by Semiconductor chips offer an efficient, unbiased, and cost-effective solution to NGS target enrichment. And our GenFisher AI probe design tool optimizes the likelihood of a successful and uniform NGS target selection. And the GenFisher probe panels are easily tunable and widely compatible with other forms of oligo probes. And as I mentioned, GenScript NGS scientific support team offers one round of capture optimization free of charge if a customer is willing to do that with us and is willing to share the capture data with the capture data of the initial design with us for us to further optimize the design for them. Now let's zoom out of NGS target selection step and focus more on the step upstream of it, that is the NGS library preparation step. As I have mentioned in the beginning of the presentation, any samples that are going to be sequenced needs to be in a form that's sequencer compatible. And for hybrid capture experiments and for whole genome sequencing studies, a pre-made library is required, and there are two common workflows to make it happen. The first one, the one on the left, starts with fragmented DNA, which can be generated by physical or chemical means. Adapters that contain Illumina sequences and sample markers or sample indices are ligated onto such DNA fragments. An optional amplification step can help increase the quantity of libraries for certain cases. For example, if the starting DNA quantity is very small, or the library needs to go into a capture process. This is also called a ligation-based method. The second workflow, the one on the right, is a transposase-based workflow. It takes advantage of an enzyme that cuts the DNA while ligating enzyme-loaded DNAs onto the cut site. This is followed by an amplification that completes all the necessary components needed for sequencing. It is a very easy and quick workflow, and it is also known as a segmentation-based method. At GenScript, we have created our own solutions, or GenTrack and our GenNature NGS library preparation kits. They integrated a series of components we have come up with and manufactured in-house. The GenTrack kit could be categorized as a ligation-based method. It takes any DNA type as input and has a wide range of input amount. The GenNature kit is a segmentation-based solution, and libraries can be made with it in less than 2 hours. And true for both kits are the fact that we have made a great number of sample indices available to our customers to pick from. And speaking of sample indices, as you know, they are used to differentiate sequencing reads of one sample from those of another sample after sequencing. So any misassignment of reads could lead to false results, especially in rare mutation calling. It also was critical that the sample indices are not in any way mixed up at the synthesis step. So oligos used for adapters are typically synthesized on columns and purified by either HPLC or page gel. Here I'm showing you a figure provided by one of our customers. It shows the rate at which they detect sample index contamination from our adapter technology and another adapter vendor. You can see that the GenScript adapters have a much lower cross-contamination rate. And for that reason, we are setting our quality control standards for our adapter cross-contamination rate at 0.01%. And that is 5 times lower than the industry average standard, which is set as around 0.5%. With high quality oligos, we offer many kinds of adapters that can be used to make NGS libraries and specialty NGS libraries. Shown here are some examples. So we offer simple one index adapters, as shown on the top of these three diagrams. And we also offer unique dual index adapters. And this is highly recommended by Illumina and also by us for all NGS applications, if you have the ability to do so. Because in some of the latest Illumina platforms, dual unique indexing will really guarantee minimum misassignment beyond the contamination happened at the synthesis step. That is more happening at the sequencer level. We also offer adapters with unique molecular identifiers or UMIs for low frequency mutation detections, as is shown at the bottom. There could be a lot to be said about how UMIs help mutation detection, and we might have a separate webinar on that. But for those who really need it, just have peace in mind that with our clean technology, the UMI and the sample indices are really going to be beneficial to your application. In addition to all of that, we offer also max customization to the adapters to our customer request, and that includes various purification methods and delivering formats. And we also can vary the index in UMI and length based on our customers' desire. And there are many other ways that we could help out here. Some other considerations that we help our customers all the time, but I won't have time today to talk about are, first of all, we offer GMP grade oligos and reagents. We offer over 100 kinds of oligo modifications as well. And we can easily make oligos that fit to your niche applications that you probably couldn't find elsewhere on the market. And lastly, I just couldn't speak enough about how customizable we are in terms of the services and products we offer. So please do reach out to us if you have any questions or special requests about any NGS and oligo related requests. So that'll be all I have for my webinar. So to quickly summarize, GenScript has both column and semiconductor DNA synthesis capabilities to better control and fine-tune your NGS panels. And GenScript offers custom and off-the-shelf NGS reagents and oligos to meet any of your sequencing application requirement and workflow. And please check out other offerings GenScript has, including more services enabled by our semiconductor technologies. And NGS or others, we have always focused on the quality and consistency of our work, of our products and of our services, and as well as staying at the cutting edge of science to be ready to serve the customers better. And with that, I would like to end. And I would like to thank you very much for your attention and your joining us today for this webinar. And as I mentioned earlier, we do, and as Irene and I mentioned earlier, we are running a free trial program, and you can find more information on our website or just reach out to our customer support. With that, I'm very happy to take any questions that you may have.
Okay, thanks very much for Josh of the wonderful presentation. And now we will attend to some questions from the audience. Okay, so the first question will be, you mentioned that the semiconductor technology can be more cost effective, and how is it compared to the price of all other synthesis technology for the target enrichment panel?
Sure. So thank you very much for that great question. So the pricing of our NGS reagents varies with a few things. For example, for GenFisher probes, things like the number of capture probes that you have or the number of capture reactions you request, they all determine the price. However, based on the information available to us from our market team and from our customers, our products are currently priced very competitively, especially so if we consider the fact that we offer free probe optimization, as I mentioned. So I encourage everybody who is interested in our services, reach out to our team, send an inquiry, or just contact your local GenScript support to find more information about the pricing and about the details of our services.
Okay, thank you. And the second question is, so our lab is actually doing amplicon-based target enrichment, and we use semiconductor technology to make amplicon primers.
Sure, that's a good question, and thank you for that. Currently, we do not recommend our customers to use oligos from our chips to do amplicon sequencing, although we do have experiences with helping a few customers do that successfully. There are some special consideration to go into our production when we manufacture amplicon primers on our chips. As I mentioned, we have tremendous flexibility as we have both column synthesizer and chip synthesizer. So we believe for amplicon sequencing, we can provide a better solution with our column synthesizers. So feel free to reach out to us, and we can maybe have a discussion with you to find out what might be the best for your project and scientific questions to answer.
Okay, thank you, Josh. The third question is, since library preparation by documentation seems easier, faster, and automation compatible, why not always documentation such as GenNature if it's easier and quick?
Awesome question, thank you. I personally like the documentation for workflow very much as well, but one obvious reason that it does not fit everybody is that it does not work with some certain DNA sample types. As I mentioned, the documentation workflow includes a fragmentation of the DNA. So it is not a great fit for those sample types that are already short by nature. For example, the circulating cell-free DNA, which is used in many non-invasive diagnostics. So for them, you know, the documentation workflow is not the best fit. And for also certain FFPE samples, documentations may not work either. In those cases, we recommend our GenTrack library preparation kit.
Thank you. And the fourth question is, when you show the target enrichment efficiency, and there's some data for flank 0 BP and flank 150 BP. Explain what's the difference of those two data?
Oh, sure. Oh, sorry for the confusion. So for the 0 BP flank, a base in the sequencing data is considered an on-target base only when it falls into the target region. As you can see, this is very strict. But for 150 BP blank, a base that is within the 150 BP upstream or downstream of the target region is also considered part of the target when calculating on target. This is mainly to accommodate the case where an NGS molecule partially overlaps with the target region. So when such molecules are captured, it is actually a correct pull down. So it is fair to include those whole molecules in the calculation. Therefore, it makes sense to expand the target region a little bit when doing the calculation.
Okay, thank you very much for explanation. And then the fifth question is, you mentioned that GenScript also have universal blockers, and could you introduce more about it?
Sure thing, yeah. I wish I had more time to get into the details for that. Thank you for asking that and allowing me to explain more. As I mentioned, these blockers are used in the hybridization process. We actually spent a lot of time to design our blockers, and we came up with a novel chemistry that is different than everybody else on the market, as far as we know. It is designed to be compatible with sample indices of any length. So currently, the common barcode lengths are 6 nucleotide, 8 nucleotide, or 10 nucleotides. So we have tested and shown internally that our blockers work with them all. And actually, in theory, it should work with any lengths, either it's 12, and beyond. So it is truly universal. I think that's the real benefit of using our blockers, and that's something we take a lot of pride in.
Okay, thank you. And the sixth question is, so how long does the GenFisher hybridization process take?
Sure. The current protocol recommends a 16-hour hybridization, or you can just leave it overnight. There is detailed protocols available online, or if you can just reach out to us, we will provide that to you. But I just want to make one more comment. That is, we are launching a performance equivalent 1-hour hybridization protocol very soon. So stay tuned.
Okay. The seventh question is, how is the compatibility of GenFisher panel with other hybridization kit in the market?
Sure. As I mentioned, we have our GenFisher Hype and Wash kit. I believe the compatibility is to a certain degree, but I want to mention that our design tool and our design algorithms are based on the conditions and ingredients of our own system. So for optimal performance, I still encourage our customers to use the whole GenFisher solution. Although it might be compatible, I think some pilot experiment are needed to really make the whole thing compatible and fit your application.
Okay, thank you. And then this is the last question. How long does it take to make a custom panel by GenFisher, and what is the general process?
Sure. Typically, we turn around our oligo pools made by our semiconductor chips within a week. But in terms of capture pools, it depends on the number of probes and the number of reactions you request. We guarantee a 4 or 5 week turnaround time generally, but so far for our customers, we have been able to deliver in less than 3 weeks. And in terms of the flow that you order, I think the simplest way is for sure to contact the email that I list here to get things going, or just contact your local GenScript support.
Okay, thank you. That's all for the question, and today's webinar is over. And thank you very much for your time, and we really appreciate that you attend this webinar. Please visit our website or contact us if you have any questions. questions or need more information. And please also check our website for the free kits offers, and we will be very happy to assist you your NGS related research in the future. Thank you very much.
Thank you, everybody.